Welcome to today's webinar, Getting Started with Serverless Architectures. Our presenter today is Andrew Baird. Andrew is a solutions architect at Amazon Web Services in our Atlanta, Georgia office. He has a broad background in software development with experience in areas including distributed processing workflows, e-commerce applications, and public APIs. In his role at AWS, Andrew works alongside AWS customers in the Southeast US to help ensure their architectures are designed using AWS best practices. Today with us, we also have Stefano Bulani, Product Manager, and Vyam Nagrani, Product Manager. They will engage with you and answer your questions throughout the presentation while our presenter presents. Andrew, welcome, and now pass the floor over to you.
All right. Thank you, Ryan. And hello, everybody. Thank you for joining today's webinar again. Again, my name is Andrew Baird. I'm a solutions architect for AWS out of Atlanta, Georgia, and we're going to help you get started with serverless architectures today. So to begin, we're first going to set some context to describe where we're coming from to show why serverless architectures on AWS are the next evolution of application design. Then we'll cover the services that enable that transformation. Then I'm going to give a live demonstration of creating a serverless application and discuss some of the other examples of serverless application patterns. And finally, we'll discuss some best practices for you to keep in mind as you move forward with designing your own serverless applications. So first, let's backtrack a little bit to provide some context about how, even though the value of building with AWS Lambda is revolutionary, it's actually a very natural next step in application design patterns. One application pattern that perhaps many of you have experienced in your past, and hopefully it's stuck in your past, is the monolithic architecture. Here, there's a holistic application that's deployed as a single unit on shared infrastructure. Its tightly coupled components perform many different functions that are maintained by a wide array of different development teams. Deployments are extremely risky and disruptive, and if any application component's deployment fails, the whole deployment needs to be rolled back. So deployments rarely occur, and they require an intense amount of centralized approval and coordination. By now, many organizations have recognized the negative impact that this application pattern has on the speed with which your development teams can deliver new functionality. Moving from the monolithic pattern, one of the most popular architecture patterns for many years and still today is a service-oriented architecture. Here, the components are decoupled and communicate with each other via web service APIs. This picture is one of the most common examples in a service-oriented architecture approach, the multi-tiered architecture or the N-tier architecture. In it, the user experience is delivered on the front end by an application that's considered the presentation tier, could be a website or a mobile application, for example. The core business logic resides on the server side as part of the logic tier, and any data that needs to be persisted resides inside the data tier. The pattern that the service-oriented architecture encompasses allows for two really important things, among others. First, the infrastructure is decoupled. So your deployments can occur independently, and scaling and resource consumption can be managed independently as well. And second, development teams can be highly specialized. Now your development teams can be filled with developers that have really specialized skill sets that are well suited for the area of the application that their team owns. So what you're left with is a smaller ownership with deeper and less broad technical skills. So faster development processes, smaller, more stable, and hopefully more frequent deployments. Finally, a pattern that's become really popular in the last couple of years is the microservices architecture. Here, the same tenets of a service-oriented architecture are still valid, but components are broken down into smaller, single-function modular web services so that the benefits we described of SOA are amplified throughout the entire application. If you're working in a centralized organization today that's pretty happy supporting a monolithic application still, this might look a little complex to you, but you've got to remember that in order to support SOA or microservices architectures, there'll likely be a breaking apart of your organizational processes as well to help reap the benefits that these two application patterns provide. So in reality, there may be a small development team whose responsibilities for supporting are just limited to this tiny subset of the entire application architecture, and they can be really, really deep on what that functionality is. And the SOA pattern has been a staple for so long and has so many millions of applications utilizing it that the tools that have been built to help you implement SOA apps and support them are extremely vast. They're extremely proven. And many of the same tools that were built for SOA already lend themselves well to the microservices approach as well. And AWS itself has helped too. There's a lot of different features and services that AWS itself has created to make creating and supporting web services-based applications easier. I mean, web services is even part of our name, so you know that this pattern is something that's important to our customers. But many of those tools and innovations are still coupled to a shared dependency that needs to be supported. And of course, that dependency is servers. All of the complexity, all of the responsibility that servers introduce to your environment are still your responsibility. There are tools and entire industries whose entire value propositions are about addressing just one of these questions on the screen. And you as an application owner have to be able to answer every single one of these questions well. And that's not to say there aren't tools and strategies for answering all of these questions. There are, and I think running on top of AWS gives you the most and best tools for answering them well, but why care? Why care about answering these questions? If you could architect to be serverless and use everything you've already learned about designing service-based applications without the need to manage server-based architecture or server-based infrastructure, that would be pretty compelling, I would think. You can have your application operations be fully managed, no provisioning infrastructure, high availability built in, no patching, no monitoring operating systems, no patching, and also when creating web services, a lot of the code that your development team will be responsible for writing is relevant to the web services paradigm itself. Running a web server, exposing an API, marshalling requests and responses. By architecting to be serverless, your developers can really focus on the core business logic that matters to your application. And finally, the serverless approach to applications will allow the applications you build to have their scaling managed for you as well, no matter what that scale is. So first, let's talk about the core service that's going to enable these benefits for you, and that's AWS Lambda. You can think of Lambda as a serverless event-driven compute service or a microservice without servers. Each Lambda function you create can be thought of as a microservice within a service-oriented architecture. So I'll explain Lambda. I'll give a brief overview of how I think about Lambda and describe 4 different components that make up the Lambda-based application. And we'll jump into each one of these components now. First and foremost is the Lambda function. This is the heart of AWS Lambda. A Lambda function is the code that you write, the AWS security wrapped around that code that you write, and the resources required to execute your code. The code that you write for Lambda can be today in JavaScript, Python, or a JVM-based language like Java, Scala, or JRuby. And your code doesn't need to be literally a single function. While there will be a single function or method that defines where execution will begin in your code, this is called the handler function. That single function can depend on other functions, native binaries, code libraries. It can make external web services call. This is really your code. Keep in mind that the code execution for your Lambda function today is limited to 5 minutes. The next piece of the Lambda function is the AWS services that your code function will have the ability to interact with from a security perspective. This is defined by assigning an IAM or Identity and Access Management role to your Lambda function that dictates which AWS services and resources your code is allowed to integrate with. If you're familiar with what IAM roles do for EC2 instances, it's the same concept. And we'll talk about the power this holds for a Lambda function more during the demo portion of the webinar. Finally, the amount of resources that your function needs to execute, as well as the amount of memory, is defined by the amount of memory you allocate to that function. And the amount of memory that you allocate to your function will also define the amount of CPU time and network bandwidth allocated to your code as well. The second component is an event source. So for the code that you've written and would like to have execute, the event source will define how and when that code executes. There are a number of different event sources available today on AWS, and that's continuing to grow at a really rapid pace. Each different event source type will define the data and metadata that's passed to your function so that it's able to process with all of the context it needs for your application. So for example, if you'd like your code to execute whenever a new object lands inside an S3 bucket and you choose S3 as an event source, when your Lambda function is triggered, it will be provided metadata like the user identity that uploaded the object, the bucket the object was created in, and the key and the size of that new object as well. And also, for example, if you choose Amazon API Gateway as your event source, your Lambda function will receive all of the HTTPS request details it needs to process that API request. The next component is the AWS Lambda Service itself. So this is where the magic happens. The Lambda Service is responsible for taking the code that you've uploaded and provisioning it onto the Lambda infrastructure that we manage for you and providing you an API to directly invoke your Lambda function. The service is also responsible for making sure that your code is executed for each and every event that you configured as an event source for your function, whether that be once a week when a new report lands inside an S3 bucket, every time somebody speaks your application's invocation name to Amazon Alexa, or thousands of requests a second that your public API receives. And finally, it provides you some out-of-the-box operational capabilities to monitor your function in CloudWatch and a logger object that will stream any log statements you make from your code to CloudWatch logs. Last is the function networking environment. And this defines what your code has connectivity to, and there are two broad options here. First, there's a default networking environment where your code function has access to the internet but no private connectivity to any of the resources running inside your VPC. Second, your Lambda function could be provisioned inside your own customer-created virtual private cloud. And here, you'll choose which subnets your function will execute within. It will consume private IP space within those subnets. And the connectivity from the function will follow the route rules you've configured inside your VPC and the security groups you've assigned to your functions. Public internet access for functions deployed inside VPC is accessible via NAT, and we encourage the use of our NAT gateway service for this. So it's important to note that this affects the runtime environment of where your code is executed, but invoking your function still occurs through the public AWS Lambda APIs or via the event sources that you've configured. And this happens regardless of if the function is deployed inside a VPC or the default networking environment. So because of these factors, if your function doesn't really require any connectivity to private network deployed resources inside your VPC and internet access is permissible, the default option is a good place to start. And this is a configuration you can change over time for existing functions. So hold on, you might be saying, wait. Serverless might be kind of a new term, but there are lots of ways for me to build applications where I don't have to manage a server already. Aren't all of those examples serverless as well? And that's true. There are a lot of ways for you to abstract away servers today and build applications that don't require you to manage server-based infrastructure. So what's unique about Lambda? Lambda allows you to work with a model that provides a really amazing balance between abstraction and control. You get to be abstracted away from all of the undifferentiated heavy lifting of server-based infrastructure, but you get full control over the code required to run your application. All of the practices and tools that your developers are already using for code creation and code management can still be used before deploying that code to Lambda. Second, security is AWS's #1 priority, and it always will be. Using Lambda means you get native integration with AWS features and services like IAM and VPC that make implementing security best practices easier than ever. Lambda is already part of many mission-critical applications that AWS customers have built today. Next is the pricing model. You pay per function execution with AWS Lambda. When you provisioned a server that none of your users are interacting with, you're still paying for that unused capacity, but not with Lambda. There's no concept of paying for idle capacity. There's no commitments you need to make to that capacity. And there's a gigantic free tier available. The first 1 million function executions with AWS Lambda are free per month, and the Lambda free tier does not expire after 12 months like other AWS free tiers. And next, there's already a booming community around Lambda that's there for your support, and there's a lot of great documented answers for a lot of the questions you might run into when you're first starting out. And then finally, the functions you create with Lambda will be co-located on the AWS platform with all of the other services and functions at your fingertips. You could write a simple API, a really simple code function that's deployed and managed by the AWS service for you that directly integrates with a gigantic relational database that's deployed with Aurora. That's pretty insane. You could have fully managed infrastructure with just the little bit of code that you need to write deployed next to the entire suite of services that we bring to the table. Because when you're building an application, compute is just a really small piece of what your entire application needs to be able to do. There's a lot of different serverless options on top of AWS, and a full application is going to need to take advantage of a broad range of these different services, from machine learning to storage to APIs to user identity management, to databases. There are a lot of great options that are fully serverless for you to take advantage of. So next, I'm going to give a quick overview of an example serverless architecture that our customers built on top of AWS today. So this is a real production architecture from the AWS customer PlayOn Sports. They gave a really great reInvent topic and reInvent talk on their Lambda architecture if you'd like to hear more details. But in brief, the architecture allows end users who are streaming live video via laptop encoders to upload that to stream it to S3 via HLS and have those chunks land in S3 buckets, triggering a cascading set of Lambda functions to transcode those video chunks into various formats and storing them in a separate S3 bucket where their end users who are viewing the videos are able to stream the video in near real time. So this is a fully serverless architecture that would have required polling mechanisms or message queues managed by a set of processing servers, all before Lambda came about. But now, not only does the compute happen on top of serverless infrastructure with Lambda, but the entire workflow is completely event-driven and managed by the Lambda service itself. So you might be saying, that's a really awesome example. It's pretty interesting. Once you've got a firm grasp on the power of Lambda, you should really think about ways in which you can build event-driven architectures and gain the value that those types of application architectures provide. But you might also be saying that gaining approval for or internal understanding at your organization for what an event-driven architecture looks like could be a complete nightmare, and you've got a lot of teams already set up and skill sets developed for building service-oriented architectures and service-oriented applications. So that's great. Service-oriented architectures still work, so let's build those. And the service that enables that with AWS Lambda is Amazon API Gateway. Amazon API Gateway is a fully managed service for hosting HTTPS APIs on top of AWS. It allows you to create APIs through the typical mechanisms that you'd like to integrate with AWS, whether it be the management console, CLI, APIs. If you prefer infrastructure as code, you can use Swagger definitions to export API definitions, and we have tools available for you to import those Swagger definitions. You can bring your own custom domain names and then choose what your API will integrate with, and you can configure it to integrate with AWS Service APIs, other backend web services, or a Lambda function. You can publish those APIs and manage the version control of them, click button single deployment, allow developers on the front end to begin integrating with mock responses while you're still developing full backend logic, and then manage the security and the access to your APIs through custom authorizations with AWS Lambda or natively with IAM and AWS SIG v4, as well as provisioning API keys for any external integrators that you have coming to your API. So next, I'm going to do a live demo to give an example of how to build a serverless application on top of AWS. And this isn't the architecture that we're going to build. If you've ever built a web application on top of AWS before, this might be a general pattern that you're familiar with, where static content is stored inside of Amazon S3, and all of the dynamic content is routed separately through API calls. But today, the API calls that our HTML file will be making will be to a serverless backend using Amazon API Gateway, whose API calls are processed by AWS Lambda, and data persisted inside of Amazon DynamoDB. So once we're completed, we'll have a fully scalable, managed application that requires no server-based operations on my part. Okay, now if we can switch to my screen, I'll begin sharing. So here's the very basic application that we're going to walk through today. Very simple website, because the use cases will vary a lot from audience member to audience member on the webinar today, so we're going to keep things really simple. I've got a serverless shopping list here, and the goal of the application is to allow users to visit the site, enter specific shopping list ID, enter items one by one that they'd like to add to their shopping list, and then retrieve their shopping list from the back end later when they go shopping. So pretty simple. If we take a look at the source code for this, and I'll make my screen a little bigger for those, so it's not an eye test. Pretty simple stuff. Everything you saw on the screen, a couple text boxes and buttons. And then the API calls that will be made by the two buttons associated. So some pretty simple HTML and JavaScript. One HTTPS post for when items will be added to the list, and one HTTP get for when a user would like to retrieve their shopping list from the back end, being made to an API gateway API I have deployed here. So some of the application I've pre-baked already, and this includes the backend DynamoDB table, a very simple table called shopping lists. And shopping lists has a single primary key called list ID, which is a string, and has a pretty small capacity for read capacity and write capacity. But knowing that if my application ever needed to scale and the DynamoDB table needed to scale with it, I'm just a single API call away from having it scale to be able to receive the amount of traffic that I require. Inside the table, I've pre-baked just a single item with a list ID of test and a couple items that I've added to the shopping list. So if I enter the shopping ID test and try to retrieve my shopping list, you'll see the API call be made through your typical browser debugger, and the items that have been added to the shopping list are retrieved from the backend database table. Okay? So let's take a look what we have inside of Lambda already today. So right now we just have a single Lambda function to retrieve a shopping list from the backend database. Now I'd like users to be able to add new items to the backend database as well, so we're going to create a second Lambda function right now to allow users to do that. So in order to do so, I'm going to create a new Lambda function. And when working through the console, you'll immediately get presented with a wide number of what we call blueprints. And these blueprints will provide you a set of sample code to provide details and examples for how to do a lot of common tasks that Lambda functions are utilized for today. But for this example, we're going to skip this step and upload our function directly. So the code that I've written is in Java, and I'll give a brief glimpse into what that code looks like in a second. So here's our shopping list code. And I won't spend too much time on this for the non-Java folks on the webinar. But it's very simple, and it's the thing I'd like to leave you with, that this is standard Java. The code is fully at my fingertips. I've got full access of the JVM to write whatever code my application requires. So the shopping list application is going to utilize a data object or domain object called a shopping list that just contains two different variables, the string list ID and a list of strings that represent the items in my shopping list. Next is the backend code that's going to integrate with DynamoDB, and here I'm using the standard AWS SDK for Java to integrate with the DynamoDB client and the shopping list table that you saw inside of DynamoDB. And then a couple small functions that integrate with the SDK to call DynamoDB APIs on the backend. So for example, in order to add an item, I'll provide the list ID of my shopping list, the item I would like to add, and the logger object that Lambda provides for any log statements that I'd like to make. And then finally, I'll integrate with DynamoDB to put a new item inside of DynamoDB with the string list ID and the shopping list item that has been provided to the function. And finally, the last class that I'd like to show is what represents the handler function. So inside this class, add item handler, I have a function called add item. And I mentioned during the overview of Lambda that while a Lambda function encompasses all the code that you've uploaded, there will still be a single place where code execution begins. That's called the handler function. So for Java, the handler function that I'm going to be using is called add item, and I've defined my own request input, a standard Java object defined here, and the context object that Lambda is going to provide with other metadata about the context of the execution that's happening. And again, the code that I'm describing isn't too important, and it will vary depending on if you're using one of the JVM-based languages or Python or JavaScript. But Now that you have an idea of what the code looks like, I'm going to jump back into the Lambda console and create the Lambda function in order to add an item to DynamoDB. So we're going to call this Serverless Shopping List, add item. We're going to add an item to DynamoDB. I have code that I've pre-built and uploaded to S3, so I'll be able to take that code I've uploaded to S3 and Lambda will be able to ingest it and use it as the code for this function. So I have the URL for where that code is living today. And here is where I specify to Lambda what my handler function is. So when a Lambda execution occurs and this function is invoked, where in my code should execution begin? And in Java, that's done by providing the package name, the class, and the method name of the function that will represent the handler. Next, I'll choose the IAM role that will define the security that my code has and which AWS services it has the ability to integrate with. And you may not have noticed, but maybe you did, while looking over the source code itself, I'm able to freely show it to all in attendance because there's no concept of security itself within my code. The DynamoDB table that it's integrating with, I'm not managing any AWS keys, any secret keys or API keys myself. All of those things will be managed by the role that I'm wrapping around this function. So it's a really powerful decoupling mechanism for all of the source code that you write with Lambda to have its access control for AWS be managed by something that's external to the code itself. So your developers don't have to manage any sensitivity around what those credentials are doing, how they're stored, and all of that security can be audited and tracked separately as part of IAM. Next, I'll leave the default settings for now for the amount of memory and the timeouts associated with my function. And then last, I can choose the function networking environment where my function will execute. So here's where I'd have the ability to pick one of my own VPCs in order for execution to occur inside a private networking environment. But I don't need that today, so I'm going to leave it as the default no VPC. Review the info I provided and create my function. So now I have a new function that's created. The next thing I want to do is test that the function is going to succeed. So here I have the ability to configure a test event and trigger it. So I have a pre-baked test event that I can try out and replace the JSON here. So I'm going to be using the same test list ID and adding the item bananas to it. So we'll save it and test it. And I haven't done any, the handler function that I've created for this example is just void, so you'll see a null response here, but you've got full control over what the response body looks like as well. Just for this example, it wasn't a necessity for me. So if we go back to DynamoDB and view our table, you'll now see that same item that exists, and bananas has been added to the list. So great, we've got a working function now. Now, in order for my front-end web application to be able to integrate with this function, I need to be able to put an API front-end in front of the function. So we'll do that through Amazon API Gateway. So I already have a pre-baked API that exists that was allowing me to retrieve a shopping list, but now I'm going to add the API that enables users to add new items to their shopping list. So this is how the API looks today. These are the resources that have been defined as part of this API. There's a list resource, and below it there's a list ID sub-resource. And that list ID is within curly braces to indicate that this is a path variable that will vary from user to user. And on that sub-resource, the get HTTP method is enabled so that if a GET request comes in, we will process it, and it will integrate with the Lambda function that is defined here. So now we're going to create a new API that represents the ability to add items. So we'll do that by adding a new sub-resource under a specific list and create that resource here. And we'll call this resource items and create it. And because this will give users the ability to add a new item to a shopping list, I'm going to create a new HTTP method and use the post method. Now, when creating a new method, I'm given a number of options for what my method and API are able to integrate with on the back end. You see these 4 options here. And today, we're going to integrate with that Lambda function I just created. We are running inside of US East 1, and I'm going to reference the Lambda function I just created, and we'll save it. Now that we've got a new method created, this screen gives us an overview of the different places where API Gateway has the ability to touch a request to response as it travels through the API request lifecycle. So on the client side, to the method request that's been received, to integrating with our backend Lambda function, to touching the response that's coming back from Lambda, and then finally at being able to modify the response and the HTTP information before that response is sent back to our end clients. So for this case, because we're creating an HTTP API that is a post body, that is a post request, that has a path variable of list ID, I need to be able to extract that list ID and provide it to the Lambda function I'm integrating with. And with API Gateway, this is done by using what's called mapping templates. So to create a mapping template and modify the request that's being sent to my backend Lambda function, I'll click Integration Request here and create a new mapping template. So my mapping template and my API is working with just the content type application JSON. And rather than having the input from the client side just be simple pass-through to the backend Lambda function, I'm going to create a new mapping template to allow that post body that's being sent to Lambda to be modified from what was originally sent to API Gateway by the front end. So here's what the mapping template looks like that I'll use today, and I'll briefly explain it. So here, this just defines what the JSON structure will be that will be accepted by the Lambda handler function and how we'll transform it from what's been sent to the API Gateway front end. So it's just a simple JSON object that has the list ID, and the list ID will be pulling out a specific input parameter called list ID, and this is representing the list ID that was passed in as part of the URI path by the end client. And then next, we'll be passing the specific item that needs to be added, and we'll do that by pulling out the JSON object called item that's been passed into the API. Okay, we'll save this mapping template. And now we're going to test our API. So we provide to you as part of API Gateway the ability to directly test before deploying to make sure that everything you've created is going to behave the way you expect. So we'll use the same test list ID, and we'll use a sample request that I've created here to add the item grapes to the DynamoDB table. Get the same null response because, again, we're just returning void in this example, but you have full control over the way that that response body would look should you need to do so. So let's go back to our DynamoDB table. Our same list of items. And now we see grapes available as well. So we're pretty happy with our API now. I think we're ready to deploy it. So we'll do that now. So we click the Deploy API button, and now we'll deploy it to what's called a deployment stage. So depending on which part of the development lifecycle, you may have different API stages available that represent those various stages of development, whether it be development or QA, test, production. You're able to differentiate your different API stages the same way, which will be branched according to the URI path by stage before any of the resources are listed. So here we're going to deploy to the same dev stage. We've created the add item API, and we've deployed it. So here's the stages view that gives us a glimpse into where our API is deployed. Close the magnifying here. And that's where our front end will integrate with. And with API Gateway, should you need to, you do have the ability to bring your own custom domains as well so that you can use your own corporate domains for your API endpoints. And here you'll be able to see things like the ability to generate SDKs so that your front-end developers will be able to integrate with direct objects rather than making HTTP clients themselves. You can export Swagger definitions of the API stage that you've just deployed and see a deployment history of the API deployments you've made in the past and perform rollbacks. So now that we're deployed and we have the new ability to add items, let's take a look at our site again, and we'll refresh it. And we'll use the same list we've been using, and we see all of the items that we've added to our list. And now we should be able to add new items directly via the web application as well. One thing I've forgotten, and I need to step back to do so, is because we're accessing this API through a browser, we'll need to enable what's called CORS, cross-origin resource sharing. So if I go back to my API and view the resources, the browser needs to be able to make an options request to my API to ensure that my API will allow that API call to be made. So in order to do this, what's really simple is that API gateway enables the ability to do this just via a couple clicks. So we go to the resource that we'd like to enable CORS on. We click Enable CORS. And this will make all of the modifications to our resources and the options HTTP method in order for CORS to be satisfied by most common browsers. So we'll click Yes and replace them. And now we're set to deploy again. Always something interesting during a live demo. So we'll deploy again. And now, if we refresh and give it a minute to make sure the deployment's occurred, now we can see that our request succeeded, and if we get our shopping list, we can see some things being added, and it looks like some folks are taking part as well. So let's use a new list, add a new item, and get my new shopping list, and you can see it there. So we've got a fully working web application that's integrating with DynamoDB on the back end with fully serverless-based logic tier. Okay, great. So now I'll jump back into the presentation. Okay, so you've got a good example of what a serverless-based web application would look like. Let's talk about some other patterns that have been popular to utilize a serverless pattern with as well. So the Microservices Architecture, which we've described before, obviously very applicable to what we're doing here. Microservices are really just Lambda functions with the API gateway front end in front of it. Next is a mobile backend, where your mobile app can integrate with API gateway and Lambda and take advantage of our SNS service to do push notifications to your mobile app on the front end. Next is a real-time analytics engine, where you can use Kinesis, our real-time data ingestion service, as an event source for Lambda, and have Lambda process in parallel and in near real time any processing that needs to occur for those data points that have been ingested by Kinesis, storing the data in a backend data source like DynamoDB for things like visualization. Now we'll talk about some best practices. So for AWS Lambda, some best practices to keep in mind is to limit your function sizes. Don't let your function uploads with Lambda become your new monolith. Remember that first invocation can take time, especially with Java where a new JVM needs to be created. So it's a great solution to not only keep your function sizes small, but in order to take away that first invocation penalty, introduce a schedule Lambda function that will hit the other Lambda function every few minutes to keep it alive. Next is don't assume your function container is going to be reused. Your function should be stateless, but take advantage of container reuse when it does occur. It can be really great for your performance. So things like loading configuration, keeping connections alive, any in-memory caching you can do, all great things you can do to take advantage of when a Lambda function container is going to be reused. The next thing worth calling out is that you do have scratch space available on disk. Each function has 500 megabytes on a TMP directory that's available for each function, and this could be something that allows you to keep resource utilization down by offloading some things from memory during processing. Next, we'll talk about some Amazon API Gateway best practices. First and foremost, use mock integrations. You're going to see a ton of benefit to the speed with which you can develop your logic tier using AWS Lambda and API Gateway, but pass some of those benefits along to your front-end teams as well. And you can do this by using mock integrations with API Gateway to allow them to begin their front-end development while you're still developing your Lambda functions on the back end. Next, combine the use of API Gateway with Cognito, which is a user identity management service that we provide to have really powerful access control paradigms that allow you to define specific IAM policies that have end-user specific access control policies based on Cognito identity. So it's a little deeper than the topic that we want to get into today, but take a look at Cognito for user management for these serverless applications, not just for mobile cases, but general user identity management. Next, decoupling is a key part of the serverless architecture. So decoupling everywhere you can, and one of the ways that you can do that is through mapping templates. Don't have your Lambda function responses be fully coupled with the API gateway responses that your clients are seeing. Introduce mapping templates wherever you can within reason so that should there be any changes that happen on the backend Lambda function that would be not backward compatible with anyone on the API front end, these mapping templates will be the first place that you could catch something like that. And next, if you're going to be using API Gateway across multiple AWS accounts that you own, use the Swagger import-export capabilities for cross-account sharing. Finally, some additional joint best practices across serverless applications in general. First is use really strategic, well-thought-out naming conventions. You've got a lot of different things that you have the ability to name within this environment, including Lambda function names, your IAM roles, API stages, all of those things. And once you have naming conventions built around them, you can create automation. So whether that be similar to EC2 tags for billing and chargeback purposes, whether it be automation in terms of continuous integration and continuous delivery, use those naming conventions to build a lot of automated capabilities. Next is externalizing authorization to IAM wherever you can. So I think the most profound part of this is what I demonstrated in the source code, how there's no concept of security baked into my source code itself. You can externalize all of those things to IAM. Next is another mechanism for decoupling is you may be tempted when creating your IAM roles for your first set of Lambda functions to just reuse the same IAM role across your set of Lambda functions that are used within the same app. I really recommend that you decouple your Lambda function and your IAM roles and have a one-to-one relationship between Lambda function and IAM role, because even if at the beginning everything is defined as least privilege, as soon as one of those Lambda functions evolves and needs connectivity or access to a different AWS service, and you need to add that permission into the IAM role, all of a sudden you've also given that access to all of the other Lambda functions that share that role. And then the last thing that I'll mention is while scaling is fully managed for you as part of these services, there are some initial limits that are put in place to both protect the services as well protect your bill. So if you plan on adopting serverless architecture patterns with Lambda and expect a large scaling event to occur, you should engage AWS support before those events to make sure that the throttling limits which are in place are going to be elevated enough to be able to manage the amount of scale that you expect your application to take on. So I'll finish by just having a call to action. I gave you a brief overview today and some best practices and a really quick demo of how easy it is to build a serverless application using AWS Lambda and API Gateway. So go build something yourself. You've got a use case in mind, I bet. Go get your hands dirty and play with Amazon API Gateway, integrating with a serverless function in Lambda and storing any persistent data that it needs inside of DynamoDB. Thank you. So I'll ask each of you to remember to fill out the polls on the left side of your screen, and we'll take a brief 1-minute break before diving into some of the QA.
Thank you for a great presentation. At this point, we're going to move into live Q&A. So Stefano and Viam have been engaging the audience and answering questions throughout the presentation. So please continue submitting those questions, and we will have about 15 minutes to reply to some of them verbally. Also, please reply to the 3 poll questions on the left-hand side. Your feedback will help us with future webinars. So at this point, I'm going to hand it back over to Andrew.
Okay, thank you. So I'll pick a couple questions here and go through them for the group. So the first question from Kyle is, what is the difference between Lambda and EC2? So while both services are compute-centric services that AWS provides, the main difference is that with EC2, there is a virtual server that you're able to deploy and fully have root OS access to the server, and all of the aspects of management and operations and choosing operating systems, all of those things are fully the customer's responsibility with EC2. With Lambda, all of the infrastructure itself is managed by the service for you, and you don't have access to the underlying infrastructure. You provide the code functions that you'd like to have executed to the service, and all of the infrastructure management is handled by AWS. The next question from Billy is about, will the source code for the demo be available? And that's a great suggestion. I'll work with the team internally to see if we can make the source code that I used today and the different assets associated available so that folks who attended the webinar or view it on YouTube will be able to find it as well. Okay, the next question from Bhushan is, in the demo, where was the DynamoDB connection string stored? Was it inside my code? And the answer for this is because I was using the AWS SDK, all that I needed to do to connect to DynamoDB was create a DynamoDB client object and provide the table name that I was going to be connecting to. And this again is one of the really powerful things within the serverless architecture pattern. That's all I needed to provide, because once I deployed my Lambda function that was running that code, it would be deployed on top of my own AWS account with the IAM role that wrapped around that Lambda function. So that would be the only DynamoDB table within that region with the same name. So you could take, theoretically, the same source code that I wrote to connect to my shopping list DynamoDB table, deploy that Lambda function within your own AWS account, and should you have a shopping list DynamoDB table running within your own AWS account, it would be able to connect to it without having to make any configuration changes at all. It's all handled by the AWS SDK and the IAM role that I've wrapped around the Lambda function. So the next question is there any benefit to assigning more memory than the Lambda function actually uses at runtime? So for example, if a function is only using a certain amount of memory that's pretty low, what are the benefits if you allocate more than that to your Lambda function? So the answer to that is it depends. So the amount of memory that you do allocate to your function, I briefly mentioned, will also determine the amount of network bandwidth and the amount of CPU that's allocated to your function as well. So even if you have a really light memory utilization Lambda function that requires a lot of network bandwidth for whatever reason, allocating more memory to your function will give you more bandwidth as well. So it's a single dial, but it will impact a couple different resource mechanisms or resource meters as well. The other thing is if you're working with Java and you'd like the startup time of your JVM to be a little quicker, this could be something that is shortened as well. Okay, let me grab another question. So question from Peter, is there a need to warm a Lambda function if you're expecting a big load? Or in other words, is there a delay when going from 0 to 20,000 calls an hour? So if you do expect a large scaling event like that, again, I do recommend that you engage with AWS support. But the thing that we recommend most customers do, if you would like to not have to worry about the initial function execution time, is to set up scheduled Lambda functions that will invoke your function for you to be able to make sure that there's function containers available for when the real load begins. But again, the best answer here is it will vary by use case and what type of load you expect. So we really would like you to reach out to AWS support whenever you have this type of scaling event in your site of vision. So question from Radek. Is there any limitation for using third-party libraries like Python? So the answer here is no, not really. You'll have full control of the function execution environment, the source code that's uploaded to AWS Lambda. Whatever your code needs to depend on, whether it's an external web service, whether it's a native binary, whether it's a code library, as long as you upload those things with your Lambda function code or import them into your code once it's running, or integrate with them via web service call, whatever you need to do from within your function, you'll have the capability to do it. So Karen has a question about spinning up many different Lambda functions can really wreak havoc on a connection pull from MySQL. How do you manage this? So one of the ways that you can manage this is if you have a set of Lambda functions that represent a microservice that's integrating with your MySQL database. If you front that with an API gateway endpoint, we do have the capability to allow you to define what the throttling limit is for that API as far as request traffic is concerned. So if you only want to be sure that a certain amount of traffic is reaching those Lambda functions and in turn reaching your MySQL database, you can set throttling limit on your APIs that are in front of these Lambda functions to ensure that you've got the ability to manage the amount of load that's hitting your backend. Question from Honor is, how can I schedule Lambda functions to execute periodically? And that's a great question. So that is one of the event sources that AWS Lambda does support. So while there are a number of different examples for event-based triggers that other services can use or API calls can integrate with a function to execute, you do also have the ability to create what's called a scheduled Lambda function, and where you'll be able to define a cron-like schedule that defines when that function will execute. So yes, you do have the ability to schedule a Lambda function to execute periodically based on some schedule. Okay, question from Kirill is, what is the best way to use DynamoDB as a database with a serverless architecture? So that's a pretty broad question and will really depend on the type of application that you're building. But all of the best practices that we build out with DynamoDB will still apply to the serverless use cases. And a couple of things that I'll highlight are, one, choosing a hash key for DynamoDB that's going to be well distributed. So while DynamoDB gives you the ability to infinitely scale and have that scale be managed for you, it's really important to choose a hash key so that the different partitions for how data is stored by DynamoDB will be spread across the entire table. So pick a really unique hash key that's going to have variance between the different items that's stored. And the second thing that I'll call out is take a look at fine-grained access control with DynamoDB and combining that with Cognito user identities and the IAM policies that you'll create related to Cognito users. This will give you the ability to define really specific records and columns that different tiers of users or specific users will be able to query inside a DynamoDB table. So look at those two things, making sure that the hash keys you choose have a lot of variance and are going to well partition your data, as well as fine-grained access control, and having the fine-grained access control policies you use for DynamoDB refer directly back to Cognito user identities that you'll have on the front end with your APIs. Okay, let me grab another question here. So next question from Brian is, do Lambdas in a VPC have access to private data center resources behind Direct Connect? So I think you'll find that when you deploy Lambda functions within VPC, you'll find behavior that really behaves as you expect it would based on the configurations you've made inside your VPC. So the traffic will route the route rules that you've defined. The security groups will be respected. Traffic will funnel through NAT gateways as you've configured them. So if you've defined the routes to allow that connectivity to occur, that's really up to the way that you've configured your environment. Okay, I think we're going to take one more question. Let's see. Okay, so Ethan has a question. Are there AWS specific tools for measuring various Lambda function performance metrics like time, memory, etc., without having to code those into a Lambda function itself? So yes, AWS Lambda does provide out-of-the-box metrics which are stored inside of our CloudWatch metrics and logging service. So if you create Lambda functions. You'll be able to go into your typical CloudWatch console or integrate with the CloudWatch APIs and see metrics around performance, memory utilization, things like that. But really the thing to keep in mind is to take advantage of the speed with which you're going to be able to develop with AWS Lambda and follow all those best practices about logging and metrics gathering that you may have been cutting corners around because of the time with which it was taking you to develop applications before. So use that logger object that we give you out of the box and integrate with CloudWatch from inside your Lambda functions. But again, to answer your question, Ethan, yes, there are metrics that we provide out of the box associated with Lambda functions. Okay, I think that's all the time that I've got today, so I'll kick it back over to Ryan to wrap things up.
Okay, great. I'd like to extend a special thank you to our presenter Andrew for his time and a great presentation, and also to Stefano and Guillaume for answering the audience's questions. If you have any comments on our previous and upcoming webinars or suggestions on the topics you wish AWS can cover in future webinars, please feel free to email aws-webcasts@amazon.com. Your feedback will help us to improve our future webinar programming. Thanks to our audience for taking the time to join us today, and enjoy the rest of your day.